Hello viewers, in today's class we are going to discuss one important application of Lagrange's mean value theorem, right? And here we have to prove this inequality involving inverse trigonometric functions, right? So here we have to prove this inequality, that is tan inverse x2 minus tan inverse x1 is less than the difference of x2 and x1, that is x2 minus x1, for all values of x2 which are greater than x1, right? So Lagrange's mean value theorem has wide applications in proving different inequalities, and here we'll prove this inequality using Lagrange's mean value theorem, right? So before taking up this problem, let us first take the statement of Lagrange's mean value theorem, right? See, we know that if we have a function, say y of f of x, which is defined in its domain D, and if we take the interval say a comma b, right? So if we take this function in this interval, and if this function satisfies these two conditions, that is f of x is continuous in the interval a comma b, and f of x is differentiable in the interval a comma b, right? So here we have the closed interval, here we have the open interval, right? So if we have a function y is equal to f of x defined in some domain D, where this interval is defined, that is a to b, and f of x is continuous in the closed interval a comma b, and f of x is differentiable in the open interval a comma b, then there must exist some point c which belongs to this interval a comma b, such that the derivative of this function at this point c is equal to f of b minus f of a divided by b minus a, right? So here we'll make use of this result to prove this inequality, right? So for this, what we will do, we'll define an appropriate function, right? So here let us define a function, say f of x is equal to tan inverse of x, right? So here we have this function, that is y is equal to f of x is equal to tan inverse x, and this function is defined in this interval, that is x1 comma x2, right? So here we have the interval a comma b, here we have the interval x1 comma x2, right? And provided that x2 is greater than x1, right? Or in other words, we can also say that x2 minus x1 is greater than 0, right? So the difference of x2 and x1 is always greater than 0, right? So now what we will do, let us see whether this function satisfies these two conditions or not, right? So here we see that this tan inverse x is continuous in its principal branch, that is f of x is continuous in the interval x1 comma x2, right? And if we find the derivative of this function, then we'll get f prime of x is equal to the derivative of tan inverse x, which is equal to 1 over x square, right? So here we can easily see that the derivative of this function, that is tan inverse x, it exists in the interval x1 comma x2, right? So our function y is equal to f of x is equal to tan inverse x, it satisfies the two conditions of Lagrange's mean value theorem, that is f of x is continuous in this interval which may be the principal branch of this function, that is tan inverse x, and this function f prime of x is equal to 1 over 1 plus x square, and 1 over 1 plus x square, it exists or defined in this interval x1 comma x2, right? And moreover, we know that the principal value branch of tan inverse x is given by this interval, that is minus pi by 2 to pi by 2, right? So now these two conditions are satisfied, hence there must exist some point, say c, which belongs to this interval, that is a comma b. In this case it is x1 comma x2, and this point, that is x is equal to c, is such that f prime of c is equal to f of b minus f of a divided by b minus a. So f of b is f of x2 minus x1. Here we have f of a is f of x1, then we have x2 minus x1, right? So now f prime of c can be obtained from this expression. So if we take x is equal to c here, we'll get 1 over 1 plus c square, right? And f of x2 is obtained by taking x is equal to x2 in this function. So we have tan inverse of x2 minus f of x1. So again f of x1 can be obtained from this function by taking x is equal to x1. So we have tan inverse of x1 divided by x2 minus x1, right? So now we have to arrive at this inequality. So what we will do, will make use of this result, right? See here, this point x is equal to c, it lies between x1 and x2, right? Okay, and here if we see the expression for f prime of c, this is 1 over 1 plus c square, right? And here we see that c square plus 1 is greater than 1, right? Because c is some number and c square is always a positive quantity, so c square plus 1 is always greater than 1, right? So what we will do here, if we take the reciprocal of both sides, then we can have 1 over c square plus 1 is less than 1, right? So this is the important step here. See, c square plus 1 is always greater than 1, right? So the reciprocal of c square plus 1 is 1 over c square plus 1. So this is less than 1, right? Okay. So now what we will do, we'll take this value of 1 over 1 plus c square over here, right? So what we will get, we'll get tan inverse of x2 minus tan inverse of x1 divided by x2 minus x1 is less than 1, right? Okay, so now see here, x2 minus x1 is always a positive quantity. Why? Because see, x2 is greater than x1, so the difference x2 minus x1 must be greater than 0. So we can multiply both sides of this inequality by x2 minus x1, right? So when we multiply both sides by x2 minus x1, we can safely get tan inverse of x2 minus tan inverse of x1 is less than x2 minus x1, right? And see, this is our desired inequality, right? So viewers, this is how we get this inequality when x2 is greater than x1, right? Okay, now see, from this inequality we can also get an important inequality, right? How? See, if we take x1 is equal to 0, right, and x2 is equal to x, then we have the interval x1 x2 is equal to interval 0 to x, right? Okay, so if we take x1 is equal to 0 here and x2 is equal to x, then see what we get from this inequality, right? So here we'll get tan inverse of x minus tan inverse of 0, and here we have x2 minus x1, so this is x minus 0, right? And here tan inverse of x, tan inverse of 0 is 0 and x minus 0 is x, so we can get tan inverse of x is less than x for all x greater than 0, right? Because see here we have x2 minus x1 greater than 0, right? And if x2 is x and x1 is 0, then we have x minus 0 is greater than 0, so we have x greater than 0, right? So viewers, this is how, by using the Lagrange's mean value theorem, we have first derived this inequality, and then we have derived this important inequality by taking x1 is equal to 0 and x2 is equal to x, where x is greater than 0, and we got tan inverse x is less than x, right?